Hello and welcome to Bay College's online lectures for intermediate algebra. In this video we're going to talk about section 8.7, which deals with exponential and logarithmic equations and the change of base. Now the change of base is the tool that we use to solve exponential and logarithmic equations. In some cases we'll need to use a calculator when we're dealing with logarithms or exponents. And being that our calculators can only do common logs and natural logs, we have this tool called change of base that gives us a form that we can put in there regardless of what this base might be in the problem. So if we have a log of some base b, it could be any number, of some other number as long as it's within our domain, we can rewrite this log using the change of base formula, which is the log of a over the log b, the base. One quick way to remember it, whatever the base is has to go in the basement of your fraction. Think of it as the upstairs and the basement. So we can write it as log a divided by log b, now these two quantities. Now one thing we want to kind of be aware of is this order. This is not a single log anymore, it is the quantity of this log divided by the quantity of that log. And notice that our base now is 10, something that we can put into our calculators, base 10, and that's what our calculators can work with. Now we also have another option, and this is generally my go-to because, you know, I'm only two letters to write when I put it on the board, but log base b of a, we can use the natural log of a over the natural log b, the natural log of the base. And remember, in this change of base, the b is in the basement of our fraction. And we could actually change the base to anything. I could change this to a log base 2 or a log base 5. As long as the bases top and bottom are the same, we can change it to anything we want using this formula right here. So let's look at an example. We have log base 5 of 89. And in this example, maybe it's something I want to find the value of, so I'm going to put it into my calculator. And I'm going to use log base 10. I'm going to change the base to log base 10. So I'm going to take log base 10 of 89, and notice because this is our common log, I don't have to denote what the base is. We have to assume 10, divided by log base 10 of 5, the base of the original log. Now this is a quantity that I can put in my calculator, and sometimes when we're using our calculators, we've got to worry about order of operations because our calculators follow those religiously. They never vary. So sometimes when we put it into our calculator, it's best that we use parentheses. So I would start with the parentheses, put in log 89, close the parentheses, divide, parenthesis, log 5, parentheses, when I put it into my calculator. And when I do so, I'm going to get a value, an approximate value, because I do have to round at some point, of 2.78895 to 5 decimals. And if you put that in your calculator, you should get the same value. Your calculator will probably extend it out a little further, but we're just going to round to that. Now here's a log that I can do in my head. I can look at this and say, well, a logarithm asks me 2 to what power is 8? And I know that 2 to the third power is 8. 2 times 2 times 2 is 8. But what if we use change of base? Does it hold true even though we already know the answer? Well, if I use change of base, I'm going to use a natural log here. ln of 8, this value, over ln of 2. Now if I plug this into my calculator, I'd be sure to use parentheses around the ln of 8, divided by parenthesis ln of 2, close your parenthesis. And if I hit enter, my calculator is going to give me the value 3, because this is the exact value. We didn't have to round it, it is 3. So we can see that even though we intuitively may know this answer, our calculator still holds true using change of base. Change of base is a powerful tool. But what if we have something like this? We have log base 2 of 40. Well, if I think about it, 2 to the 5th power is 32. 2 to the 6th power is 64. So whatever this value is equal to is somewhere between 5 and 6. But it's an estimated value. If I want to plug this into my calculator, maybe I want to use base 10 log. Log of 40 divided by log of 2. Now it's base 10. I can plug it into my calculator and I can get a value. And it should be between 5 and 6, and when we plug it into our calculator, we get 5.32192. So we have this approximation. Now we can use this concept to solve other equations, especially when we're dealing with the natural log. We can rewrite these into logarithmic equations, and then maybe use change of base. Maybe we won't have to. Notice the base here is already e. That's something I can plug into my calculator. So I'm going to say, well, e to the negative some power equals 0.04. So I'm going to rewrite this as a logarithmic equation, and I can use natural log because that's my base. If I take the ln of this side, and we know the properties of equality, what I do to one side, I have to do the other. So I'm going to write it ln of that side. Now, ln of e, we can use our power rule of exponents, bring that out front. Well, ln of e is 1. And negative x times 1 is just negative x. So we can also think of it, because this base and this are the same, it simplifies to 1, negative x. That's all that's left over. Equals ln of 0.04. And now I can say, okay, well, in order to get x by itself, I just have to change the signs. So I get x equals negative ln of 0.04. And this is a value that I can plug into my calculator. But we'll leave it in exact form for now. X equals negative ln of 0.04, something that we could find a value because our calculators do natural logs. All right, let's look at this next example. I'm going to erase a little bit here. If you need to see it, you can always back the video up. But what if we have a problem like this? Well, I look at this and I say, hey, this has a base of 5. 5 is being raised to some power, and that's where my variable is. So I want to solve this. Well, the first thing, I want to isolate my base. So instead of 2 times this quantity, I'm going to divide both sides by 2. So divide that by 2, the 2's reduced. Divide that by 2, I get 12. Now, I can say, well, I could take the log base 5 of both sides. So let's do that. If I take log base 5 of this side and log base 5 of this side, we can reduce this. This simplifies to just 2x minus 1, or 2x minus 6, excuse me. And we can think of it this way using the power rule. We bring it out front. This would reduce to 1. 5 is the base, 5 is the argument. So we could get the same result either way. Equals log base 5 of 12. That's what I have over here. And then we can just isolate this. I'm going to add 6 and then divide by 2. Now, if you're wondering how I jumped to this here, I added 6 to both sides, log base 5 of 12 plus 6 more, and then divide by 2. So I divide this by 2, I divide the 6 by 2 to get 3. So I skipped a step in simplifying, but I did point it out there. Now, if I want to find a value, I would have to plug this into my calculator. All right, well, log base 5 of 12 is something I cannot plug into my calculator, but I could use change of base here. All right, so it's good practice. We can do change of base. Essentially, I just have to take 1/2, that's dividing by 2, of, maybe I use the ln of 12 over ln of 5, and then add 3 to that quantity. So, make sure when you plug it into your calculator, you do that. Now, that's a long and drawn-out way, but here's the thing. We can do change of base all the way back here, and it's kind of using the properties of equality. So we took log base 5 because that was my base of the power, but what if I said, you know what, I eventually want to be able to put this into my calculator, so I either want to use common log or a natural log. Well, at this point here, what if I took the ln of both sides and then simplify? So I'm going to erase this for a moment and work through this problem. And we'll see, okay, well, ln of 5, that I can bring this out front using my power rule. And I'll just put parentheses around it. ln 5 equals ln of 12. So that's just using that power rule of logarithms, right? If we have a logarithm to a power, we can multiply that power. Now, here, my x is here, I want to get this by itself. I can just simply divide both sides by ln of 5. And if this looks familiar, that's a great thing. Guess what we just did? We did change the base when we took the natural log of both sides. When we had log base 5 of 12, if we do change the base, we get ln of 12 over ln of 5. Now, at this point, I can add 6 to both sides and then divide by 2, and I'm going to get half of 6 is 3, and half of this quantity is multiplying by 1/2, 1 times the top, 2 times the bottom. Essentially, we get the exact same result we had before. So we see that it does hold true, and by taking the natural log or common log, at this point, we're going to save us some time of not having to do change of base at a later point. But here it is, something we can plug into our calculator and find the exact value. And if we do plug in the exact value, I think we get x equals 3.77198. Okay? Yeah. All right. Now let's move on to this next example. We notice we already have ln of x, and we're going to use something very similar. Here we took the ln of both sides. Here we already have a natural log. Well, how can I get rid of a natural log out of an equation when I want to solve for x? Well, the thing I can do is I can identify the base. The base is that natural number e. So instead of taking the log of both sides, I want to get rid of the log. So I'm going to raise both sides to the power of e. Now, if we remember our properties of logarithms, e to the log of that base, or a base raised to the log of the base, reduces to 1 again, and all we're left with is x. So I'm going to think of this as just 1x. So I get x equals e to the -2nd, and that is something we can plug into our calculator. Our calculator has the e key. We might have to hit the shift function on our calculator, and then the ln key, which has this above it. And if we do plug that in, we're going to have to approximate, and I wrote it down on the board there. We get 0.13534. All right? Let's look at this example here. Now, in a previous video, we talked about writing as a single logarithm. That's something we have to do here. I only want one logarithm. I notice they're of the same base, and we have subtraction. That tells me I can divide these logarithms. Log base 4 of this divided by that argument. So we get x plus 7 over x. This is written as a single logarithm. So all I did was combine them. So now I have this equals 1. Now, one thing I can do is I can say, well, 4 to the first power, rewrite this as an exponential equation. 4 to the first power is this argument here, x plus 7 over x. Now, this is an equation I can solve for. But I want to, well, 4 to the first, just 1, or 4. But I want to identify something just for a moment here. I see an x in the denominator, and we should always concern ourselves with domain. So right now I'm going to say x not equals 0, because I can never divide by 0. So if I work through this and find x is 0, I'm going to say, wait a second, x can't be 0, it's not within our domain. So now I can multiply both sides by x. And I can get my x's on one side, subtract x from both sides, and divide by 3, and I get a final answer of x equals 7/3. And if I were to plug this into my calculator, I could go ahead and do this, and then maybe do a change of base at this point, and check my work. Make sure that 7/3 work. And if you do plug that into your calculator, you'll find out that 7/3 does in fact hold true. It doesn't make this negative, and it doesn't make it undefined. It is within the domain, and it is equal to 1 when we check it. All right, let's look at this example here. Now here we have two logs base 3, so we want to combine them. Since it's addition, I can just multiply them. Log base 3 of x times this quantity. I'm going to distribute it. So now I have a single logarithm. Now I can eliminate this logarithm by writing it as an exponential equation. My base is 3, my power is 2. So I get 3 squared equals the argument x squared minus 8x. Now this is of course 9, 3 squared is 9. And essentially what I have here is a parabola, and hopefully we all recall how to solve parabolas. Set them equal to 0, and then attempt to factor them. If factoring don't work, maybe you can complete the square or use the quadratic formula, but this one factors real nice, so let's go ahead and factor it just for review purposes. The factors of -9 that sum to -8 are x minus 9 and x plus 1. So we can use the zero value theorem here and say, well, x either equals a positive 9 or a negative 1. Very important to check our work when it comes to logarithms. If I plug in 9, log base 3 of 9, well, I know 3 squared is 9, so this value would be 2 if I plug in 9. 9 minus 8 is 1, log base 3 of 1. Well, the log of 1, regardless of the base, is always 0. So if I have this value plus that value, is it equal to 2? Well, 2 plus 0 is in fact equal to 2, so I know the value 9 works. But we have another value. We need to check it. If I plug it in, log base 3 of -1, I'm taking the log of a negative. That tells me that's not within my domain. I cannot take the log of a negative number. That tells me right away that I don't have to check it any further. The answer is x equals 9. It holds true, and we know it works, and it's within the domain. So that's some examples of working with exponential and logarithmic equations. This has been section 8.7. Thank you for watching.